Welcome to the webinar series of the Center for Subsurface Energy and Environment. I am Nicolás Espinosa, a faculty and investigator at the center. And today I'm filling in for our director, Matt Bachholz. In case you want to know more about the center, here is our web address where you will find more information and our contact information. In the center, we have 26 PIs between faculty and investigators, and we work in a variety of subsurface applications, combining several disciplines and tools. We work with federal agencies and industry, and one of the ways that we collaborate a lot with industry is through our industrial affiliate projects. So here's a list of all the industrial affiliate projects if you are interested in any of them. Again, I encourage you to check our website for more details. Today, we're going to have Professor DiCarlo, but let me remind you that if you want to check previous seminars, please check our YouTube channel, Texas CSEE, where you will find previous webinars. And I also encourage you to follow us in social media like Twitter and LinkedIn, so you'll get notifications about the next webinars. And actually here we have them already listed for October 1. Dr. John Olson is going to talk about predicting hydraulic fracture geometry in shales. And on November 5, Dr. Gelshad and Aikobul will talk about a very timely topic, which is geological storage of hydrogen. So our speaker today is UT Professor David DiCarlo, who holds a PhD in physics from Cornell University, and whose research focuses on applying advanced experimental techniques to understanding fluid flow in hydrocarbon reservoirs. Let me remind you that he will be answering questions at the end, but I encourage you to go ahead and write your questions as they hit your mind. Professor DiCarlo, the floor is all yours.
Thanks for everybody showing up today. I'm David DiCarlo. I'm a professor here at the University of Texas at Austin, in part of CSEE, Center for Subsurface Energy and Environment. Glad to be talking to you today. Today, my talk will be on basically increasing initial production from fractured wells or altering the fractured fluid properties. This work was supervised by me, but was mainly done by my students Xiao and Tianbo, and also my postdoc Rafael Longoria was a big driver in getting all this work done. In hydrocarbon production, we know that unconventional reservoirs are kind of the big deal right now, but if we're going to make them work, and the only way that people make them work is to do fracturing, you have to fracture these reservoirs to obtain economic production. Different fluids have been used. You can use water, you can use gas, you can use foam, you can put surfactant in your water. All different possibilities for these fracturing fluids. What's going to be the best for basically our initial production and maybe our total production? This is always a big question. Okay, so what happens? Why does it make a difference which fracturing fluid you use? The main reason is it can invade or leak off into the formation, and this could reduce our initial oil production rates, maybe even our final oil production rates. So what I'm going to talk to you today is try to understand what's going on with this fracturing fluid. I'm going to talk about experiments, not models. We'll do a little bit of modeling, some theoretical, some numerical stuff later on. But the main thing is driven by experiments. And basically the questions are, how much damage does this invaded fluid cause to the oil production? How does this change with the fracturing fluid? And what happens with the damage in time? Again, this is a general picture of how you do a fracturing. This is a cartoon where you have your surface facility, you draw your horizontal wells, you put your horizontal fractures in here, and this is a side view. This is a side or a top view of the whole thing where you have your well going here. Here are your planar fractures taking place. And again, the reason we do this is because it greatly increases the contact between the formation and the wellbore, and even in our low perm reservoirs, we can get enough flow if we get enough surface area. Okay. But unfortunately, this fracturing may result in significant fluid losses to this formation. And what happens to this fluid? How does this affect our production? So let me just draw a little picture here. We'll take a little scale in from instead of one of these big fractures. I'm going to take here and blow up this little zone here. It's just one fracture here. Here's the wellbore. Here's the fracture. During fracturing, again, you're pumping in water here or gas or foam. The higher pressure is making this fracture extend here, propagating the tip through the overpressure, but also this fracturing fluid is invading the matrix as this fracture propagates down the screen. And then after you fracture it, you've put in some sand or some proppants to keep it open. After the well is when you reduce the pressure. Hopefully that keeps it open. That's not what I'm talking about today. What I'm going to talk about today is basically what happens at this fracture face here in terms of what this fluid does to the oil production. Okay, so here's again the big picture of that one fracture. What I'm going to talk about, what we're going to do experiments is we're going to cut out another little section here. And the way we're going to do our experiments is see what happens when we go 1D into and out of our core. So we're going to take a core here to look at just a small part of it, and we're going to inject the fluid into our fracture face and take it back out and see what happens versus time. So now this is actually, we do experiments. I can't take that whole big block of reservoir into my lab, but I can take a small core. Okay, I'm taking a core that's much more permeable with the reservoir, but I'll get to that later. I just want to understand the basic physics of what's going on. And so what we do is we take our core. Our experiments consist of taking a core, and Xiao, Tianbo, or Raphael fills this core with oil. Then they put in a small amount of water, gas, foam, whatever fracturing fluid we want to look at, to partially saturate the core. And then we flow oil back through during the production phase and try to measure how the pressure changes versus time and how the saturation changes in time to understand how the invaded fluid affects the oil permeability during the production. So this is our production step. So we'll measure the pressure drops, but we also measure saturations by putting the core here inside the CT scanner, turn vertically here. We have our pumps to move our fluids in. We have our piping to get it all the way in. Here's a little cartoon. Again, we're putting in oil from one direction and the fracturing fluid from the other direction, and we're having our little invasion zone right here. Okay, and so we're going to measure the pressure drop. We're going to measure the saturations. Let me show you what the results of some of the measurements are. These were the earlier measurements done by Tianbo Liang. A lot on these plots. Let's start on the right-hand plot. The right-hand plot is basically after we apply the fracturing fluid. In this case, it's just water. So these first experiments were just water. We put water in a certain amount, and you can see that you get water invading part of the core. Okay, and then we start flowing the oil back in this direction, and we can see the water saturation change with time. I'll break down the details of this change in a bit here, but basically we can measure this versus time using the CT scanner. Along with this oil, along with measuring the water saturation, we can measure the pressure drop, and this is shown on the left. So this is pressure drop versus time. It's in these black points here. Okay, there's black pressure trace here. And we do lots of these different experiments. We try different fluids. We try different amounts of water invasion. We try different amounts of permeability. I'll show you all the details to begin that in a second. But the main factor is that what you can do, we see in all these experiments is during the flowback, we see this region where we see a plateau, where we see basically this water affecting the flowback affecting the production of the oil. When the pressure drop is higher, we're having less, we're doing a constant flow rate here, but basically if you had a constant pressure drop, this would be a lower flow rate. So in this case here, where the pressure drop is higher, the water is blocking the flow of the oil. But eventually it clears at this point here and drops down to basically some value which stays here. And this took about 5 hours to clear for this experiment. We always see these plateaus. Okay. And so we want to understand how long it takes for this to clear and get back to our maximum production rate of a reservoir here. So we want to measure this time in different cases. But one thing we noticed, and Tianbo noticed this to begin with, is that when this plateau seems to end here, is exactly where we start finally clearing some water at the fracture face. So basically, this is a little bit of a capillary end effect that's keeping the water in. The assumption or the hypothesis is a capillary end effect that's keeping the water in this little bit of the fracture face. And once it breaks after 5 hours after the flood, which is basically here, then the pressure becomes less. And so finally, this last saturation trace where the water saturation is in this magenta or purple color here, we have very high production rate. Okay, so that's our hypothesis. To check this hypothesis, we don't need just to do one experiment. We have to do a whole bunch of experiments. And so the question was, how does this scale with rock and invasion depth? Okay, so Xiao did a whole bunch of different experiments where he varied the permeability and he varied the length of how much we're going to invade for a certain permeable rock. Okay, and as you lower the permeability, as we go from a 14 millidarcy, again, this is a higher permeability than you're going to see in unconventional. We'll talk about that in a second. 14 millidarcy rock to 3 millidarcy rock, the plateau goes from a shorter time to a greater time. And also, if you invade deeper into the rock, we go at 0.83 centimeters, put in a larger slug of water, it takes longer for it to clear. And if you put a shorter slug, it takes a shorter amount to clear. Aha. Okay. So again, the hypothesis is that we need that water to clear right at the fracture face. At least that's what we saw in our initial experiments for the pressure drop to go back to its minimum value or to get the maximum production rate. So we see a certain scaling that takes place. Okay. Well, the assumption here is that basically what we see here, going back to this picture here, we can see the water going further and further into the core with time. Even though the main flow is going, the oil is flowing right to left, the water is going left to right. So this looks a lot like capillary imbibition when we see this. So let's model it through capillary imbibition. And so this clearing takes place when the water capillary imbibes further into the core, not out of the core. Okay, so the equations for capillary imbibition are well known. You can write down the mass balance equation. You can write down the flux due to a capillary pressure gradient. You can put in you get a certain diffusivity type of form, and you can you can write down the equation. We can discretize this. We can model it with our initial water block or initial amount of water in like this. And then after a time later, you can see it drop, the saturation drop. And then basically once this water imbibes enough here to lower the saturation at the front, at the fracture face, we're gonna assume that's gonna be its clearing time. Tau W is what we call it. And then greater than that, the water imbibes even further and the water block is basically cleared. The maximum production is achieved. Okay, so this is what a model gives us. And again, let me show you back to the experiment here. It kind of looks like the experiment. So it seems like a reasonable assumption. Let's check to see if the model matches the data. Okay, so got a bunch of different saturation snapshots. Again, here's for 10 millidarcies, and this is 4.1 millidarcies. And you can see you get different time scales for this to take place. And again, we're looking for this dashed red line when that first drops at the point here. Okay, from the numerical simulation. And we can basically simulate that this scales in a certain direction. Okay, you can do it. And when you put in the math and you try to figure out the scaling, well, it's actually not that difficult. It's just a diffusivity. The scaling time should depend on the length of the water invasion squared and go inversely with the permeability. The square root of the permeability because the capillary forces are pulling it in. So you go to lower permeability, you get greater capillary forces. You go to lower permeability, though, it's going to take longer because it takes longer for the fluid to flow, and that ends up with a square root of permeability. And so this predicts that the scaling time is going to go as L squared over square root of K with a scaling constant factor up front, alpha, which we call alpha, which should depend on the fluid viscosity, the IFT pulling it in, porosity, all these other petrophysical parameters of the rock. Okay, so let's compare this to our data. And if we fit the alpha, but we let the scaling go as predicted by the model. And you can see here, the blue points are the data, measured data. And this is just with one alpha, we can fit all our data as a function of core permeability, as a function of the superficial invasion length, basically how far we invade. And we can see this and the plateau duration for different, this is all for one length, this is all for a different length, and vice versa. So the scaling equation works for both experiments and simulations. That gives us confidence we understand how when you invade that water or your fracturing fluid into your reservoir by the frac job, how that's eventually going to clear and get to the position where you're going to get the maximum permeability and maximum production rate. Okay. So this was done with much more permeable rocks than you see in the core, what you see in the field. The reason why we looked at this study and we wanted to see the effect of permeability is because, hey, we want to scale this to what you're going to see in the reservoir, where you don't have millidarcies, you have microdarcies or even nanodarcies. And if you take this equation and you take the experiment, you take our prefactor here, and you take basically an average length, which is going to depend on how far it invades, and we'll get to that point in a second here, from the field operations, and you take the permeability, so where you're going to have field op where you have 10 to minus 3 to 10 minus 4 millidarcies or microdarcies or nanodarcies, it is predicted that this should take 26 to 120 days to clear. And this is kind of what people see in the field. That basically after 25 days, after 100 days, everything is going to give us the maximum flow rate. Now, you may have lost some of the reservoir pressure. Of course, your production rate's gone down as the reservoir pressure that's driving this whole thing drops. Okay, but this kind of scales to what people see in the field. So this brings up a question. This is just one fluid. Maybe we should use a different fluid to do our fracturing. Maybe we can get a better production rate with a different fluid besides water, or fracturing fluid, or brine, whatever the water fracturing fluid we use. So the question is, do gas and foam invasion clear using the same physics, where the water imbibed further into the core? Is the physics different for gas? And foam is going to be a combination of gas and water. Okay, so we did experiments to do exactly the same thing, but in this case, we're not doing water invasion, we're going to do gas invasion. And we're going to do it with two different oils. One is that's saturated with the invading gas, and one is unsaturated. So the unsaturated one will tend to dissolve some of the invading gas, while the saturated one won't dissolve any invading gas because they're basically at chemical equilibrium to begin with. I'll share you some CT results of both the invasion step and the production step, and also the pressure results too for these. Exactly the same type of setup. Okay, so this is with the gas saturated oil. We invade the gas into our core. We basically try to stop at a certain place, and then we do a production step here. Okay, for the gas saturated oil, after 0.12 pore volumes of nitrogen invaded, our gas is nitrogen. Our oil is just octane here. No, it's it's pentane, heptane. Sorry. And then the production step, we basically see that when the oil is going back to this other direction, we still see a lot of gas left behind in the core. Okay, we do this with a gas that's undersaturated oil. The same amount of gas that's invaded doesn't go as far, which is not surprising because some of the gas is dissolving into the oil as the invasion takes place. Okay, and then we do the production. We see actually with time, we see a front where basically we dissolve the gas away, and eventually we get back to, after 0.7 pore volumes, we get back to the initial state. So it sure looks in this case the gas is not going away by imbibition, but it's going away by dissolution. So it's different physics that controls the clearing of this invaded fluid. At least that's what it looks like here in terms of our CT scanning. Here's pictures of the CT scanning, and you can see basically the undersaturated oil. This is the invasion step. It basically doesn't go in as far, and then you can see it basically going away when you flow back here. And this one's kind of stayed here. It stays with the gas in it. So let's not only look at the saturations, let's look at the pressure drops. And the orange data here, the burnt orange data, is for the gas saturated oil. So we see this is the baseline pressure drop that we measured before we invade our core. And this is after we invaded with gas. So we still see this extra pressure drop caused by the gas. Okay, but if we do the gas undersaturated oil, what we can see here is basically with time and almost the same amount of pore volumes we see in the CT scanner, that we see that basically the pressure drop declines. So we can see that gas causing a change in the pressure drop. And it only takes a little bit of gas to cause a change in the pressure drop, because the gas over here, even though it's a small amount of gas, it's occupying the bigger parts of the pores. So the gas, in some sense, is causing more trouble than the water when the gas is in there. Okay, but the gas clears faster, and it clears by a different mechanism that's going to scale in a different way. Okay, and so we can do here, we can plot this versus time. We can plot this versus pore volume, and the clearing takes place. Okay, we find out the clear up time scales with flow rate, not time. So again, if we flow faster or slower, it's always the pore volume over here, which determines how fast it clears up. Again, another experimental evidence of basically we have dissolution taking place, not having something that basically takes place spontaneously. The water spontaneously clears, basically. We don't even have to flow the oil back for the water to clear. So the water clears with time. The gas only clears by flowing oil back through the thing. Okay. Question is, can we model this in a simple, well, I mean, not simple, but basically a straightforward multi-phase flow physics, multi-phase flow model with gas and with dissolution? And yes, you can. You have to be careful. You can use some MOC theory, which is a method of characteristics, where basically we can assume it's a front going in and a front going out. You have to be very careful of how you handle all the compositions, because now you have some of the gas dissolving in the oil, and you can set up basically how the molar volume changes with the composition. You can put this all in a model that matches our data. You can find all the fractional flow waves, as we like to do. Those people who we like to think theoretically what's taking place, and we can model it basically either we can model analytically and can compare the model to what we see experimentally. And so this is the difference between the bottom one is the difference between the saturated oil and the undersaturated oil, the unsaturated oil, and you can see that the fronts are moving at different speeds. Again, this dark blue is the same as this dark blue, which is over here, which is passed through. This magenta here is not gone nearly as far in this case as in this case. You can see from the fractional flow, if you want to do these fractional flow plots, that this flow rate here, this is steeper, so it's moving at a higher velocity. That shock is moving at a higher velocity for the saturated case as opposed to the unsaturated case. Now, does it match the experiments perfectly? No. Our model is assuming no capillary forces in this case. For the gas, we assume no capillary forces, but there's still some capillary forces. There's still some smearing. There could be some viscous fingering going on. So we still see more smearing than the model gives us a complete shock, but it's kind of matching it pretty good. We can also, you can do the whole calculations of all your refractions and all your shocks and all these other things, which we like to do. You can also then look at the flow back using the same theory, and you can see back when you have the saturated case, you don't see any flow back here or any change in the saturation. But if it's unsaturated, we can get this dissolution front, and we can calculate the velocity of that dissolution front. And it kind of, again, matches the experiments. Not exactly. We don't have all the physics in our model, but we just have the main physics, we believe. Okay? And if we use this model, you can predict the pressure drop too, because the model is going to have a certain relative permeability. And here we can compare the pressure drop for the saturated case and the unsaturated case. And hey, actually, that's pretty close. Okay. So if our model works correctly, we think we have the physics right. It seems to match the experiments in most ways. So, but the important thing is this dissolution process scales differently for the gas than it is for the water. It scales with the production rate. Okay, it depends on the solubility of the oil, and depends on the amount of fluid invaded. Very different physics than the water. So it's going to give you a different time scale. So again, summary of what we see when we use these different fluids. Water blocking physics. Okay, the water is cleared through the redistribution or imbibition of the water, and the gas blocking physics is cleared through a dissolution process. All right, but for both of these cases, one of the key parameters for how long it's going to take to clear is the volume of the fluid invasion. How much fluid do we get in? And if you want to choose a better fracturing fluid, you want to get the least amount of fluid in. Because as we showed before in the water blocking physics, this time scale goes as the length squared. Or if you invade twice the amount of water, it's going to take 4 times the amount to clear. Okay. The gas blocking physics is all kind of linear. If you invade twice the gas, it's going to take twice the time. Both these cases, we have to be able to predict how much volume is going to invade. If we really want to compare it to the field, to what we see in the lab. In the lab, I controlled how much volume is invaded. In the field, you don't have that control. You have to put it above a certain pressure to get your fracture to propagate, and you need your fracture to propagate. And so that pressure drop is going to determine how much volume is going to invade, and also the amount of time. So instead of doing it through a constant, putting in a certain amount of flow rate, then Siao decided to do some experiments where he controlled the pressure and just to measure how much fluid invades at a certain pressure and how that's different between the water and the gas. Okay, so now this is a constant pressure is the key point right here, not a constant flow rate or amount of fluid we control. And we're going to measure the amount of fluid that goes in. So then we can take that and then we can calculate how long it's going to take to clear. Okay, so let's do single phase water invasion. We keep the pressure around 20 psi across and we can watch the water invade. What we find is the water moves at like a piston-like displacement, and it kind of invades slower and slower with time, which is not surprising because the water is going to be less permeable than our light oil that's in this case. And you're going to have a higher pressure drop because you have a multi-phase flow here as opposed to the oil ahead of this front where there's basically no multi-phase flow. A very different physics on how gas invades. The gas invades a lot faster. Okay, again, the gas is going to go in there and make the high permeability streaks. Neither of these are imbibition things. These are basically forced. And the gas moves much faster with time when it invades. Okay, so you get a different length scale in both these cases. So we also see the water invades as a piston-like front, and it's similar to the single-phase case. The gas invades with a much lower frontal saturation, and these are caused by the difference in the phase mobilities, the gas being a lot more mobile than the water. Okay. So what about all the volume of the fluid invasion for these three experiments? So one of these experiments, oh, actually, let me make a point here. I messed up the slide here. And this one did an experiment where we did foam, where we basically did both water and gas. So you can watch the water and gas invade at the same time, because not both of them are going to clear their own different physics. And so, but the question is, how far does each one get in here? So this is basically just a leak-off model. There's lots of models for leak-off. They typically have a leak-off coefficient, which goes as a square root of the pressure and has all these factors of other petrophysical parameters, just kind of like our cleanup things that we discovered here. And you can do for the water, and it matches quite well. Okay, fits pretty well. But for the gas, it doesn't fit so well when you just have single phase. For two phase, it seems to fit a little bit better. Okay, so it doesn't, it's okay in some cases, but maybe not other cases. Question, is this a result of our experimental setup or not? That's something we're still trying to figure out, because in our experiment, one of the things, let's go back to the core, the reservoir doesn't look like this. Okay, the reservoir doesn't look like a core. It doesn't look like you can control one end or the other. When you're doing this back in our picture to begin with, this fracture is going into the whole reservoir, and this invasion step isn't basically something coming out the other end. The invasion is going into basically, it's all pressure driven. Okay, this is basically locked up on the other end, and the other end isn't centimeters away like it is in our lab. The other end is hundreds of meters away or tens of meters away. Okay, so invasion still needs to be understood a little bit better here, because the lab doesn't mimic it as well as the production step. So let's look at how the scaling of the clearing time takes place here. For water invasion, you can predict this is the time it takes to clear goes as the length squared, and the length squared goes as the permeability. So the overall scaling for water, when you put the length, so this is for a certain amount of time. We're going to assume that you have that extra pressure in there for your frac job at a certain amount of time to propagate your fracture before you go on to your next fracture to propagate here. So the overall scaling for water is actually, when you go to more permeable formations, this is going to cause more of a problem, because basically you're going to invade more water. Okay, but for gas, it comes out a little bit differently when you do all the scaling here. For gas, when you go to more permeable formations, you'll still get more gas in there, but now since your production is going to be faster, the scaling rate for the production for the gas fracturing fluid is going to get smaller with permeability. Okay. So it's slightly different just because of the different physics of how things are clear. This last part here, we're just doing a lot of assumptions here for basically how fast the things are going to go in. We don't see all of it with our experiments. We still need to do a few more experiments on this, but this is suggestive of the scaling that needs to take place. So summary for water and gas invasion. What I've done today, I've presented in situ saturation for the constant pressure invasion for water, gas, and combinations where you're going to do both water and gas. The water invasion is well described by the conventional leak-off model. In single phase and two-phase invasion. The gas invasion deviates significantly from the water conventional model. It doesn't seem to be applicable for gas-based fluids. We may need a different gas invasion model. And there's also a difference between single phase and two-phase invasion. Again, how far these things invades are going to be really important for how fast it cleans up. And choosing your fluids so that you're going to invade less is going to be important for how fast it cleans up. So I'm going to get to some of these conclusions. I see I'm way ahead of time, but maybe that's good for after answering questions. And I'm glad to go back. I'm seeing some questions appear in the chat. Please, you can put those at any time. I'm going to answer them one at a time as they come through here. Let me get to the conclusions here. The most important part is a significant portion of the invaded water gas is trapped after fracturing. And this can cause your oil production to change over time. Basically, it can reduce your oil production to begin with. If it's a water invasion, this is cleared by spontaneous inhibition. The experiments, the model, the scaling with the permeability, the scaling with the length invaded, all matches up spontaneous inhibition. Okay, so when you do a water frac, you actually want this water to invade further into the reservoir. This gas block is cleared by dissolution during the oil production, which means that it doesn't resolve spontaneously, but it does resolve with production. And it's all going to depend on your solubility of your gas. If you use a propane gas or if you use a hydrocarbon gas, it's going to be a lot more soluble than if you use nitrogen, but nitrogen is still going to be pretty soluble. Again, it depends on the exact oil that you're going to have. Okay. Invasion dynamics for water and gas are also, again, we need the volume here. The invasion dynamics for water and gas are also likely to be different in this case. And again, we have to do a few more experiments on that type of setup. So we'll find out that the gas invasion does not follow the leak-off model. Importantly, for talking to a general audience, we'd be really interested to compare this to field production data. Now, there's a lot of caveats with that. A lot of times I've looked at some of the models that people have used for unconventional production. A lot of times they throw out a lot of the early data because of all these multi-phase flow physics effects. You have to be very careful with all the other things going on, with how the pressure wave is propagating to produce the reservoir. When you produce a reservoir, you're not always producing with a constant pressure gradient. Actually, you're never doing it with a constant pressure gradient, but maybe you can couple these things in together with enough production data and assumptions about the pressure gradient. It's going to take a lot of data and some data analysis and some data analytics to figure that out, to see if these models seem to match what we see in the field. So I want to thank you all for your attention today. Again, I've been here for 35 minutes. I think it's fine. It's better for more questions. I'm happy for questions. Again, I see them popping up here. Anybody wants to talk to me offline about different things they're seeing in the field, different things they're seeing, questions that they have from their operations, feel free to contact me. There's my information, DiCarlo@mail.utexas.edu. And again, I'll be looking at some questions here. Thanks for your attention. So the first question is from Anonymous. Thanks for sharing a great lab and modeling work. I would like to get your thoughts on the overall application of these learnings from low permeability matrix flow to tight formations, where the true matrix flow might be different. So the low perm 7 millidarcies, which is we did our experiments on, to tight formations, again, these microdarcies that I mentioned in the talk, where the true matrix flow might be different with no major invasion, but additional mechanisms such as rock softening, micro crack generation, benefit of imbibition, etc. That's a really good question. The questioner seems to say, hey, the physics may be different because you have these other different things taking place, like the micro crack injection, rock softening. Yeah, those things can take place. I'd love to study those. My assumption, the working assumption I've got going here, let me just answer my working assumption on this, is that even when you go to low permeability, microdarcies, nanodarcies, as far as I've seen so far, the multi-phase physics equations still seem to work, which are basically that when you have multiple phases in there, your permeability is going to be reduced, your capillary forces are going to scale with grain size, and you're always going to have mass conservation. That's what all the equations are derived from. Okay, now some of these things like microcrack generation that the questioner brings up here, or rock softening, maybe this has different changes in permeability. But let's start with the simple thing first and just scale it and see if it works. And so again, we didn't use those rocks. Why didn't we use those rocks? Well, if we tried some of those rocks, we couldn't measure any of these fluid flows. These were taking a couple days. If you go down 3 orders of magnitude in permeability, then you're talking about a couple of years to get results. And that's not really on the time scale of grad students or in any type of experimental measurements, because lots of other things can go wrong with your experiment for a couple of years. We just can't get the area. So we're relying on the equations a little bit. Now, if there was a model on how the rock softening would take place or the microcrack generation would take place and how that would change the permeability, you can kind of test that. But yeah, this study wasn't on that. Again, I'm using what I'm familiar with, right? You kind of use the tools you know. So I think it's a good question. And I think it's an important thing to look forward to. The next question was by Julio Villarreal, who's a student in our department. Good afternoon, Dr. DiCarlo. You talked about the blocking effect of gas molecules. What do you think would be the impact of an overpressured condition like seen in the Haynesville Shale with a gradient of 0.8 psi per foot for the same effect? Okay, let me try to understand the question a little bit here. First, for Julio, overpressurized condition. Well, if you're overpressured, which I mean basically the gas is undersaturated, which I mean the oil is undersaturated, which I think you mean for overpressured. I'm not exactly sure what you mean by overpressured. It could mean that your reservoir is overpressured, but you're going to have a higher driving force. It's higher than the gravitational gradient. I mean, higher than the hydrostatic gradient. Maybe that's what you mean by overpressured. Well, it depends on it really just depends on the gas solubility of the oil in the oil. And at a higher pressure, you're going to have a higher solubility. So the higher the solubility, the faster it's going to clear. And my guess is that any of these gases, when you put them in the field, they're going to be pretty soluble in that oil, except for one type of gas. That's probably the gas, the production gas. So if you take the produced gas, well, that's already going to be saturated with respect to the oil. That's not going to have it depend on, it's not going to depend so much. But maybe if you're at much greater pressure, then it can dissolve back away again. Next question is from Elowa Ahmed. He says, great lecture. Don't you think there are some limitations in scaling HF experiments from permeable core samples to tight formations? Well, let me answer that question. Do I think there's some limitations? Oh yeah, there's going to be some limitations, but we got to start somewhere. So let's start with the simplest assumptions we can to see if everything seems to match up, and then see if it does or doesn't, and go from there. Again, this was kind of asked for the first question. I'd love to do these in really low permeabilities, but I have no idea how to make that work in the lab. Again, it only works in the field because you have huge areas. The lab can only take so big of things to get enough fluid. So yeah, I do think that to summarize my answer to your question, I do think some limitations. I think that only way to go about these limitations is from basically good observations in the fields, and that's for all you operators out there. You may be finding out things here that don't match up with this. Or basically then you're left with numerics because we can't get to these low permeabilities in the lab to actually do flow through them. All right, next question is from Tony at Halliburton. How does pore size and mineralogy impact the physics associated with your proposed model? Oh, that's a very good question, Tony. Maybe I kind of went it over a little too quickly. I'm just assuming that the permeability goes as the pore size squared. It's just a Carmen-Cassini. And I'm assuming that the capillary pressure goes as the inverse of the pore size. So that's why we get the square root of permeability. So now if you have a different mineralogy, if you have a different type of rock, it's going to have I've made the assumption that we go for my carbonates are going to have the same pore structure as our shales. That's not a great assumption, okay? But the scaling will still be the same, but the prefactor may be different. Okay, so if it was actually just a shrinking of the carbonate pores, and we just shrunk it from our micron-sized pores of our carbonate to our nanometer-sized pores of our shales, and just shrunk it all perfectly down, then it would hopefully scale exactly if this physics works correctly. We don't have that one-to-one. So that prefactor of 1600, oh, I forget my units I had there for the prefactor. That's not going to work exactly. And it shouldn't work exactly because you're going to have a different pore size distribution, a different mineralogy. Again, oh, so one of the mineralogy questions has to do with wettability. And I didn't kind of touch this off in the talk. I'm assuming your rock is going to be water wet. I don't think many of these unconventionals are water wet. So that's where the mineralogy takes place. So then you might say, well, then it's all, what are you doing here, Dave? How you got imbibition, you're assuming water wet. Well, a lot of the shales are basically organic, or they have the organic part and the inorganic part. The inorganic part should still be water wet. The organic part should be oil wet. And so all this imbibition would take place in the inorganic matrix as opposed to the organic matrix. And there shouldn't be any water imbibition into the organic matrix. So then you're going to say, well, you're going to block up some of the organic matrix, the inorganic matrix. I think the inorganic matrix is the important part for the flow paths. That may be wrong. If we assume that the inorganic part, so there's a coupling between the organic matrix and the inorganic matrix, and they're kind of coupled, the water imbibes in this one, and then what we need for it to clear, we need to imbibe further, so then it becomes clear back here again, so then it can start going back through the inorganic matrix. Again, that assumption may be wrong, but someplace we're starting from. Okay, another one here from Tony. A follow-up here saying, would you kindly elucidate the conclusion that water is cleared via spontaneous imbibition? That's what we see in our experiments, in our carbonates. Okay, again, it's not the shale rock. So everything seems to match that up. If you have a model, it fits the data, it fits the saturation profiles moving, it fits the pressure things versus time. It fits the scaling with permeability. It fits the scaling with the amount of water we invade. I think it's pretty convincing, at least for our experiments, that it's imbibition. In the field, I expect to have an inorganic matrix where you're still going to have this imbibition. And one of them I've heard, again, I haven't seen the data directly, is that most of the water you inject during the fracturing thing does not come back. So therefore, it's gone in the rock. Something's gone in the rock. And then if the water likes to imbibe in the rock, and again, you actually want it to just keep imbibing typically. According to those results, are there any recommended chemicals that should be added to mitigate such consequences? Oh, you're asking a perfect question. Oh, I like this question. Tianbo Liang did experiments with different surfactants that I didn't get a chance to talk to you about today. It turns out that if you use different surfactants, it totally changes, well, not totally changes, it can change how far and how fast that water imbibes. And it also will change the saturation profile behind how much the water imbibes. We tried type 1, type 2, and type 3 surfactants. It seems that type 1 surfactants gave us the best results. We got more water invasion when we put surfactants in. You lower the IFT, you basically, what you do, you get a better flood. So you get less pressure drop affecting the water. So the water kind of goes in further because you don't have as much multi-phase flow, because it clears out the oil better when you have a surfactant. You get a really good inhibition then. But the surfactant doesn't go far. The surfactant gets left behind. And then when you get the flow back, actually, you get that water cleared out even more. So you get more water in, but you also get water out faster. But you still want that water to imbibe. Okay, you don't want to stop with you don't want to end up with a low IFT of your water inside your rock, because then it won't imbibe further. But that doesn't seem to be a problem, because the surfactant gets stripped as you're invading the surfactant. And what we see is we still see imbibition in the case, just to say. I have other papers on that, and if you can contact me offline, I can send you a whole bunch of things, and we can consider that question later on. It seems that surfactants would help you a little bit. But again, the scaling, we have not done the full scaling on that one. Okay, question from Anonymous. Great talk. Have you studied the effect of addition of wettability alteration surfactant in the liquid phase on flowback and tight formation? The answer is no, but it's a good thing to maybe to study in the future. I think for some of the wettability alteration, we need to have a correct rock that's going to have the wettability of your shales. I firmly believe the wettability of shales is very different than the wettability alteration that takes place in conventional or clastic reservoirs, or even in carbonate reservoirs, where the wettability of being oil wet and shale has to do with basically just the organic source rock. Well, the wettability changes in reservoir rock or conventional reservoir rock take place from oil being in there for a long time and changing the nature of the surfaces. So one starts with organic material. Conventional has the regular mineral surfaces in there, and then the oil comes in and changes the wettability. The second one is how we do most of our models, or most of our experiments with our different oil rocks or oil wet rocks for conventional reservoirs. So if I took a carbonate, I can make it oil wet. But if I make it oil wet that way, I don't think it may match up with the oil wet, which is the actual oil wet of the shales. I'm still thinking about how to do that. If you have any suggestions how to do that, I'd be much obliged. Or if you'd be interested in research on that, I'd be interested in see how we can figure out how to get some funding to do that work. And Julio is next question is Julio is following up for, he basically says, yes, higher reservoir pressure, it being overpressured. I don't think the question is, yeah, for the overpressure, does this change much? It's the pressure differences which are driving everything I'm seeing here. If you have an overpressure reservoir, I think you're going to have to fracture at a higher pressure just to get it in. But again, that extra pressure to get it in is going to be an extra frac pressure. I haven't thought about that deeply, because then it depends. If you have more overpressured reservoir, maybe you don't have to put in the pressure as high over the overpressure to fracture it then. So maybe you get less invasion. That's an interesting question, because there's the frac gradient and then there's the overpressure, and the amount you need to get your fractures to propagate compared to your reservoir pressure could change. So I think that might, so that would be the driving force. If you only need a little bit over the reservoir pressure to get the fracture to propagate, then you're going to get less imbibition, less forcing of the fluid in, especially the gas. But if you have a bigger one, then it's going to take more. Then you're going to get more invasion. Again, that gets at the leak off that we're trying to figure out. How fast is this really leaking off to get the length of it invading? Do you anticipate higher viscosity water-based fluids would be a net benefit to mitigate this effect? The model testing seems to support it would be mobile less, but would the increased pressure required to produce the higher viscosity fluid offset the benefit far out in the fracture field? Aha! That's a good question. If we kicked up the viscosity, what's going to change here? I haven't thought about it in a couple, I can't think of it off the top of my head, but we can model it in the sense that if you have a higher viscosity fluid, you're going to have less invasion to begin with for the same pressure drop. So you're like, oh, that's better. So you get less length of invasion. But then the imbibition is going to be a lot slower for it to clear, because you're going to have a higher viscosity. have to work out the equations here and see how the model all fits together with I think the viscosity is in there. I don't have it off the top of my head what would change. And then if you're using viscosifiers, you also have to worry about how the viscosifiers are transported within the porous media, of course. But it's an interesting question. My guess is you want to have the least amount of viscosity to begin with, just because I think a more important question for viscosity is to make your fractures as long as you want to get the more area in too. So I'm not a geomechanics expert on the fracturing and whether you use a slick water or a gel fracture. I think you want to get most area. That's the primary thing. This is a secondary effect that we might be able to change the fluids with. How do you think the wettability will affect the results in the water case? And how did you take the wettability in consideration? Again, I'm assuming that most of the flow is in the water-wet network. I'm assuming everything is water-wet. Again, there is going to be an oil-wet network in the real rocks. And the coupling between them, I really think the water is not even going to get into the oil-wet thing. So this water invasion is not a problem for the oil-wet rock. The gas invasion could be. And then, so the water is not going to imbibe into the oil-wet region at all because it doesn't want to be there, and those pores are so tight. In the flowback operation in a formation that is sensitive to drawdown pressures, there's an increased pressure differential prior to clearing the water block. Would this study tend to indicate that the potential to damage the formation may be even greater until the block is cleared? Ooh. That's a good question. So let me summarize how I'm thinking about this. So you're saying if you have a bigger pressure drop when you're flowing back, so let's just say you pull that water out as fast as you can, you get a bigger pressure. I'm going to assume no rock damage because I'm just going to assume that. I'm not a geomechanics expert here. Maybe there'd be more rock damage. Let's just talk about the fluid flow. What we see experimentally is not that we don't actually see much water come back. And you don't even want the water to come back. You want the water to imbibe in further. And actually that pressure gradient of the oil pushing out, it doesn't seem to make a difference of how fast that water invades if we're producing oil at a certain rate or if we're not producing any oil at all. So the water's just kind of, hey, there's some tight spots I can get in further in, and I'm going to keep going in. And the oil, if we're flowing it back, is just like flowing off the top. Now, initially, there's a little bit of two-phase flow that takes place. You get a little bit of flow back. If you went at a faster flow rate, you might get a little bit more flow back there. But that actually isn't much of the total amount of water that comes out. That's kind of my answer to that question. I don't know how sufficient it is, but yeah, we didn't look at the effect of the pressure drop. Because we did it without pressure drop and with pressure drop. We basically just shut it in for some of our experiments, and we didn't see a difference. So maybe if we went to a super high pressure drop, it could be a difference. But my guess is that you're not getting a huge amount of flow in the real case. All right, thanks everybody for your attention. I'm out of questions. It is almost 1 o'clock. You're probably done eating your sandwiches. I'm gonna eat my sandwich. Glad you guys all attended the webinar.